we have solved systems of equations is every single time we've solved them, we've gotten one solution. If we solve it by graphing, the lines intersect at one point. That point of intersection is the only solution to that system of equations. Well, today we're going to introduce that sometimes we have other situations. There can be two other situations. In fact, actually you've already discovered one of them. When the lines don't intersect, what's true? What do we say? They're parallel lines, which means if they can't ever, parallel lines means they can't ever intersect, right? So can they share a point in common then? No. So then we, in fact, I think on your, when you were doing this in your homework, something should have happened, and maybe you knew how to handle it, maybe you didn't. But when you're solving it by graphing and you get parallel lines, what did we say when we did assignment number 91 and you got parallel lines? What was the solution? No solution. So there can be a no solution. And then there's a third possibility where there are infinitely many solutions. In other words, every point on the lines is a solution. Not every point on the coordinate plane, but every point on the lines are a solution. And there are infinitely many points on a line, so we say infinitely many solutions. Okay, well let's just talk about when we have a system with at least one solution. So in other words, it has one solution or it has infinitely many solutions. If that's our situation, what we say is that we have a consistent system. You can count on there being a solution, in other words. It's a consistent system. And then, if it's a consistent system, then it breaks down into two other categories. If there's exactly one solution, like we've had most of the time, we say it is an independent system also then. Where they intersect at that one point, there's exactly one solution. It's an independent, consistent system. So it's a two-part name. And then if it has infinitely many solutions, or every point on the lines are solutions, we say it is dependent. So we can have a dependent, consistent system. So that's two situations. We get solution, a solution or solutions. We say, okay, well then it's a consistent system. But now I have to take it one step further. I have to decide, is it an independent or a dependent one? And then when we have, now we're going to just explore a little bit more about consistent systems, because in our homework, when you're trying to decide what type of system it is, you got to know what kind of solutions it has. So if it's an independent one, lines are intersecting. So when you're looking at the graph, let's say you solve it by graphing then, you should end up with intersecting lines. Well, what if I don't want to graph it? What if I just want to look at it algebraically and decide that they would be intersecting lines? What would have to be true for them to be intersecting? What kind of slopes would they have to have? Different. They just can't be the same, can they? They have to be different, because if they have the same slope, what's true? They're parallel. They're possibly parallel. But remember, there's one more condition for parallel. What's that? Different y-intercepts. So right now, the best we can say is that they're independent. You should have intersecting lines on a graph. Algebraically, they have to have different slopes. But then they also have to have different y-intercepts. Okay? Dependent is the same line. So if there's infinitely many solutions, one line's lying on top of the other, every one of their points are intersecting. Well, if they're the same line, what would be true about their slopes? They'd have the same slope. And what would be true about their y-intercepts? They'd have to be the same also. In other words, they have the same equation. If they're the same line, they literally have the same equation. And these lines have another name. And when we have lines that intersect in one point, we call them intersecting lines. When we have lines that intersect at infinitely many points, we say they are coincident, not coincidence, I gotta make sure I can spell it right here. Coincident lines. Coincident lines. One right on top of the other. Okay, so that's when we have a consistent system. There is a solution or infinitely many solutions. If it's one solution, it's independent. You can count on the lines crossing on the graph at one point only. We can count on them having different slopes. Or if it's a consistent system, it can also have infinitely many solutions. It's the same line. Those lines are on top of each other. They have the same slope, the same y-intercept. Well, then there's a system with no solution. We've come across that a few times, and that is an inconsistent system. So no solution, inconsistent. So what did we say? What kind of lines do we have when there's no solution?
Consistent.
No, what kind of lines are they though on a graph? Parallel. The lines are parallel. So in other words, what would we expect to happen on the graph? If we have an inconsistent system, we would expect parallel lines. And parallel lines have the what? What kind of slope? Same slope. And what's true about their y-intercepts? Different, and different y-intercepts. Okay, so there's only one type of inconsistent system, and that's when we have parallel lines, no points in common, and we don't even have to give it another name. We just say it's inconsistent because there's only one of them. It doesn't have to be separated out from any other system. Okay, so when solving algebraically, here's what we should be able to expect, which is how we've been doing them in lessons 5.2 and 5.3. Consistent and independent system. Consistent and independent. What would the graph look like again? It's up above. We just talked about intersecting line. So what should the solution be? An ordered pair. Yeah, an ordered pair. We will get an ordered pair solution. We will get an x value and a y value, and only one of each. So if you're solving it and you get an x value, or maybe you get the y value first, it doesn't matter which one, and you can go back and solve for the other. You have a x value and a y value that can become an ordered pair. So you say, oh, I have a consistent independent system. Well, if it's consistent and dependent instead, both variables will eliminate. So this is what you should have had. Something like this should have happened in one of those problems that you had in homework for today when you were solving. All of a sudden your variables should have been gone, both the x and the y. Did that happen? Yeah. But when you have a consistent and dependent system, yes, the variables will eliminate, but you will end up with a true statement. You should end up with something like 3 equals 3. That's true. 0 equals 0. That's true. But I don't think that's what happened in the one that you did in the homework, did it? Because then that would have been consistent and dependent, remember, means one line on top of the other. What you ended up with should have been on when you solve that one in the graphing assignment number 91, you got parallel lines. So then we would say, oh, okay, if I'm solving that one algebraically, again, the variables are both going to eliminate, but this time, and this is what should have happened in that one that you were doing for today, you should have ended up with a false statement. Something that didn't even make sense. Like 3 equals 6. 0 equals -4. Something that was not true. Okay, so this is just kind of like a summary of what kind of systems do we have, what should we expect, and now when we're going to practice what would happen in your homework. I'm going to show you a couple of different ways you can show your work in your homework when you're trying to decide when they're asking you to show that it has no solution or infinitely many solutions or whatever. Okay, so here's our first one. It says, show that y equals -2x plus 5 and 2x plus y equals 1 has no solution. Okay, so you have two different ways you can go about this. You can say, you know what, I'm going to pretend I'm going to get ready to graph it. I'm not going to really graph it, I'm just going to get it ready to graph, and then I'm going to compare their slopes and their y-intercepts, and that should help me decide what kind of a system I have. So method one, that's what we're going to do. We're going to get ready to graph, but not actually graph them. So I took the first one, y equals negative 2x plus 5. Is it in a nice, graphing friendly form? Yeah, ready to identify the slope and the y-intercept. What's our slope?
Negative 2.
Negative 2. And our y-intercept? 5. Okay, remember, we're going to get ready to graph, but not actually going to graph it. Our other equation, 2x plus y equals 1. Is that in graphing friendly form right now? In other words, can we identify the slope and the y-intercept at the moment? No, so let's get it there. What should we do? Okay, subtract 2x from both sides. And y is now alone, and we have 1. I'm going to change that to add the opposite. 1 plus the negative 2x. What's our slope?
Negative 2.
Negative 2. And our y-intercept? 1. Okay, so we have both of their slopes, we have both of their y-intercepts, and now without even graphing it, we should be able to say, okay, and you write this stuff down. Instead of actually graphing it, you say, oh, comparing their slopes, they are the same or they are different? Same. They have the same slope, don't they? M equals negative 2. And then you say, oh, comparing their y-intercepts, are they the same or are they different? They're different. Same slope, different y-intercepts. What would happen on our graph then? We'd have parallel lines. Yeah, we've learned that before, that means we're going to have parallel lines. And once we prove they're parallel lines, we know there is no slope, no solution. And that's what they wanted us to prove. And we did. We said, you know what, without even graphing them, by comparing their slopes and their y-intercepts, same slope, different y-intercepts, they're crossing the y-axis at different places, but they're rising and running at the same rate, then those have to be parallel lines. They're never going to cross each other. There's no solution. Okay, that's one method. You get to choose which one, I believe, we'll look at your homework in a little while, but you get to choose which one you want to use to prove it. So here's algebraically. You're like, you know what, that abstract, not being able to actually graph it and see it doesn't work for me. Well, then let's do it algebraically and see what happens. You have this choice. So this is an or. You get to do one method or the other. You don't have to do them both, okay? Method 2, solve algebraically. Substitution or elimination, a good choice here?
Substitution.
Substitution. One of the equations is already solved for y, so we would take that negative 2x plus 5, sub it into the other equation for y. So we're going to say 2x plus negative 2x plus 5 equals 1. Okay? Are those parentheses important? Can they just be ditched?
Yes.
Yeah. So we can kind of pretend they're not there? Because there's nothing up front to be multiplied and there's addition. So we're okay. So 2x plus negative 2x. They're gone. They cancel each other out, don't they? And so we end up with 5 is all that's left and 1 on the other side. What happened?
Gave a false statement.
Gave a false statement. The variables eliminated, and so we're going to write that down. We have to we justify this. The variables eliminated. Not only did we eliminate the y, which that's a good thing to do, so we can solve for the x. But in the process of eliminating the y, guess what? The x eliminated also. So the variables eliminated, and 5 does not equal 1. That's a false statement. Remember what we said on the front, algebraically. If the variables eliminate and you end up with a false statement, you have a no solution. Okay, and now we're going to practice, okay. Oh, right here. I'm sorry, right here we want to put this, when we did it algebraically, when this happens, we want to say no solution, okay? So we got parallel lines, that told us no solution. We got a variables eliminated and a false statement, no solution. And this is like our final thought here. After using either method 1 or method 2, we would say, therefore there is no solution to this, and it is what kind of a system? Jared?
Inconsistent.
It's an inconsistent system. When it's an inconsistent, does it have any other name that we need to worry about? No, inconsistent system. There's only one type of inconsistent system. Okay, so when you need to prove no solution, or you're solving a system of equations and one of these two things happens, whether you're doing it graphing or algebraically, you would say, oh, there's no solution. We always have to state what's true about the solution, and then what kind of a system do I have because of that. Any questions? Anything, any part of this you want to go back to and talk about? Okay, then let's go on to the next one. Show that y equals x minus 3 and x minus y equals 3 has infinitely many solutions. Method 1, compare their slopes and y-intercepts. In other words, pretend you're going to graph them. Okay, well the first one is in slope-intercept form, so we can go right to identifying its slope and y-intercept. What is the slope of that one? 1. What's the slope of this? The y-intercept of it? Negative 3. Because remember, this could be changed to add the opposite. Okay. How about the other equation? What should we do?
Subtract x.
We gotta get it in slope-intercept form first, don't we? So let's change this to add the opposite first. Subtract x from both sides. And now we have a negative y equals 3. And again, I'm going to change that to a negative, or add the opposite, which makes it plus a negative x. Are we done? What do we got to do now? Divide by negative 1, right? Okay. Every piece. And our equation reads y equals negative 3 plus x. Is that the same equation as the other one? Sure is. Yeah. Sure is. And in fact, they gave it to us in slope-intercept form, and then they gave us its standard form name, and when we rearranged standard form into slope-intercept form, we discovered that, guess what? This is really the same equation, just renamed. So we can say, oh, here's what happened. I don't have to graph them even. I see that I have the same slope and the same y-intercept. Thus, it's got to be the same line. One would graph on top of the other. Well, what does that tell us? How many solutions are there then? Are there any?
Infinite.
Infinitely many solutions, that tells us. Every point on those lines is considered a solution to this system. Every point on those lines. Not every point on the coordinate plane, but every point that's on those lines, one's on top of the other. They have lots of points of intersection. So that's how we would show it graphically. How would we show it without actually graphing it? Comparing the slopes and y-intercepts. How would we show this one algebraically? No. Suggestions again for how you think would be a good way to solve it. Substitution again, okay. So, because the first equation is z equal to y, we'll put it into y for this one. Now, I would suggest that we change that, rename that equation so it's add the opposite. And even probably insert a negative, put a 1 in there. So this really is the same as this. This is where some of you are having trouble with substitution when there's subtraction involved. So let's rename that as x plus a negative y. Well, a negative y is really the same as negative 1y. So now when we substitute into it, we will have x plus negative 1 times x, and I'm going to change that to plus an, add the opposite also, x plus a negative 3, and then equals, we got a 3 on the other side. So we really have here a 1x, right? So I'm going to bring that 1x down. I'm going to do distributive property. So that becomes a negative 1x. That becomes a positive 3. And what happens here with these x's? They cancel. So we only have our 3 left. And our 3 on the other side. So what happened?
Gave a true statement.
Gave a true statement after what happened? What happened
Variables
first?
were eliminated.
The variables eliminated. Let's write that down. The variables eliminated. How did I spell right? I have all kinds of trouble spelling today. The variables eliminated, and 3 does equal 3. So that tells me, oh, there are infinitely many solutions. So again, I can do one or the other. So for those of you who don't really like this all-in-one grade, doing a really graph and comparing the slope to y-intercept is going to come to your rescue today. Okay, so whether we do it method one or we do it method 2, I want us in our notes, right? Because I want you to know this is what you have to. You have to say something in your homework. You have to say, okay, well, what is the solution? What is the type of system then? Well, you've already written it twice, I realize, but there are infinitely many solutions. And what kind of system do we have then? Jared? Okay, consistent. I'll go with that because it does have a solution. You think it's independent or dependent? Dependent. Think of it like this. Independent. That means you want to do it by yourself, right? There's only one of you. Dependent, you want to rely on others. So this would be, there's more than one solution, so this is a dependent. So consistent, dependent system. So questions on that one? Okay, one to go. Show that the following system has one solution. Okay, again, compare their slopes and y-intercepts. Well, good news, they're both in. What's that form? Slope-intercept form. Awesome. The slope of the first one is -2, and its y-intercept is +2. The slope of the other one is -1, and its y-intercept is 3. In reality, tell me something. Would we even have to compare their y-intercepts if their slopes are different? We really wouldn't even have to compare them, would we? We could say, oh, they have different slopes. As long as they have different slopes, we know that they can't be parallel lines. We know that they can't be the same line. So they have to be intersecting lines, don't they? Well, if they're intersecting lines, there's going to be how many solutions? One solution. And you don't even have to find it, you guys. You don't even have to find it. Right now, you're just determining what kind of systems they are. Well, if there's one solution, one and only one solution, then at the end here, we're going to say what kind of a system is it? Now, this one's gonna make us work a lot harder. So hopefully you would make a choice in when you're doing homework and say, you know what? Do I wanna solve algebraically when they're both in slope-intercept form and I can just compare their slopes and their y-intercepts? So which method do you wanna use for this one? Elimination or substitution? Substitution again. Okay, so this would go in the other equation for y. We're doing this whether you know, in your notes you need to have it. So negative 2x plus 2 is going in for y in the other equation. What should we do next? Add 2x both sides, okay. And now we have that 2 by itself, and what is negative x plus 2x?
X.
Positive x. Subtract 3. Subtract 3. We're getting some practice still solving algebraically. What does x equal? Negative 1. Okay. And which equation do you want to use to solve for y? First one? I want to use the second one. I'm going to override you. Y equals negative x plus 3. Y equals negative 1 goes in for x plus 3. This really means the opposite of negative 1. What's the opposite of negative 1? Positive 1. And so what does y equal? 4. So we end up with negative 1, 4. We end up with 1 solution, don't we? An ordered paired solution. So whether you did it by comparing slopes and y-intercepts, pretending you're going to graph, or you solve it algebraically, when you're all done, you say there is one solution to this. Therefore, it's what kind of a system? Okay. So first of all, let's always make this decision first. Is it consistent or inconsistent? When it gives a solution, it's consistent. Think of it as, you know what, you can count on something when it's consistent. So we can count on there being a solution. And then when there's only one, remember, you can do it by myself, independent. Now, it does not matter which name comes first. I'm not going to penalize you on a quiz for saying independent, consistent, but we have to make sure that we get both things, both parts. Okay? So any questions about this part? This one. Okay. And then